Good day and welcome to this problem solving session. We'll be solving a problem from the Mechanics of Materials textbook, chapter 1. So the problem says each of the two vertical links, CF, there are two links here, connecting two horizontal members AD, this is AD, and EF, this is EG, has a 10 by 40 millimeter uniform cross section and is made of a steel with ultimate strength in tension of 400 MPa, while each pin at C and F has a 20 millimeter diameter and is made of steel with an ultimate strength in shear of 150 MPa. Determine the overall factor of safety for the links CF and the pins connecting them to the horizontal member. So the question says determine the overall factor of safety for the members, for the links for the links CF, there are two links here, and the pins connecting them. Now, factor of safety basically is a measure of how much stronger a system component or material is compared to the expected maximum load or stress it will experience in service, right? So for the factor of safety, let's call that FOS here. It's F, let's say the force, like here it says the ultimate strength in shear. I mean, well, like the force that boat will experience, I mean, the maximum force that boat will experience compared to the force in that member, right, which is CF, which is what we are looking at here. So now to determine, first you have to determine both of these, right? I mean, F, the maximum, and then the force is in that member. So let's start with the force in member CF. For us to do that, if you take a, we have to isolate this. Look at this. You see this spot here, right? We have to isolate it, and doing that, we use the known forces. The known force we have is here. You know, this is in tension. This is probably acting this way. So let's isolate this part, member EFG. So by isolating that, we have to draw a free body diagram. So I'll be drawing this below here. So let's say here, this point. So let me draw a straighter line. Here we have, there's a force here at this point. Let's call here F. Let's call here E. It's acting downwards. There's no force pulling on that point. There's a force pulling on that point, but it's downward. There's 24 kilonewton force, which is the only unknown force we have here, right? Now, since we have kilonewtons there, when we can convert that to newtons, then this we have here, it's 400 millimeters. We can turn this to this point here. So if you change that to meters, it's divided by 1,000 at 0.4 meters. If you divide this 250 millimeters to will be 0.25 meters as well. Now we have we have three forces, but only one is known, right? So to simplify the problem, let's solve by equilibrium, and you take moments about point E, right? Because we are really interested in FCF here. Take F, this is FBE. Take moments about point E. Doing that, we eliminate the need to find FBE, right? So we take moments about E equal to 0. And zoom in anti-clockwise here to be positive, right? So in doing that, what we get will be 0.4 FCF, that's distance between this point here and here, right? And the next will be this, but negative distance between here and this. So negative minus 24 times 10 raised to the power 3, converting to Newton, multiplied by 0.65, which is 0.4 plus 0.25, and that will be equal to 0. So if you compute this correctly, it will be FCF equal to you take you take this part to the other side, right, and divide by 0.4. Computing that, we should give it 39 times 10 raised to the power 3 Newton. Right. So with this now, we've gotten FCF. Which is this. Right. Now let's find the force in let's find the maximum force in those in the member CF, taking into account the shear in the pins, right? Now for that, we have, it says we have two links here. What is this? See, we have this CF, right? Now, and there's a hole which is the diameter of the pin itself, right? The question says the link is 10 by 40 uniform rectangular cross-sectional area, right? So remember from the problem, you can see there is tension in link CF. You see it's pulling upward. There is tension there. So think of that as a rectangular. That's a rectangular plate with a hole. That's a rectangular plate with a hole, right? So let me see if I can sketch that, something like this. There's a hole here. There's a hole here. So we have to find the area of this link. Now, the area of this link, it's giving us B minus D times T. T is the thickness. T is the thickness. Now here we have this is the width, right? And this D here is the diameter of the hole. So in essence, if I sketch this a little, okay, let me just show this, right? You have this here. So what this is trying to let us know is from here to here is the width, right? This one here, phi, that's the diameter. It's okay. Once you use phi, that's the diameter. So B minus D, we want to find the area of the material that can resist shear. Of course, the hole is no longer there. That's why I say B minus D, right? That's the area of the material resist shear. That's what it is, the area of the material that can resist shear. Now multiplied by the thickness, because it's going to be applying in the direction, right? So that's basically what it is. So that's why we are using B minus D times T. Now in doing this, of course, if you look at the units we have, it said there in the problem, it said 10 is here. 10, the T here is the thickness, 14 is the width, right? So that would be the width, which is 0.04, 40 millimeter divided by 1000. Then the diameter is 20, of the diameter of the pin. It says 20 diameter, that's of each pin, right? Diameter of the pin. First, what we are doing is for the area of 1, right? 0.02 multiplied by the thickness 0.1, right? Equals to 200 times 10 raised to the power minus 6 meters squared. That's area. Now this is the area, very important, area of just one link. Remember, there are two links there in the problem. There are two links in this problem. If you look at this, there is one here, so one, and there's another one behind, right? But now, of course, when you find the area of one, you just need to simply multiply to find the area of the other. Now, for the pins, you're experiencing double shear, right? There are two in number, right? One at C and one at F, right? Okay. So for the area of the pins, it either, pi r squared or pi d squared over 4, right? Is equal to pi. The diameter of the pin is 0.02. It's the same as here, same diameter. 0.2 squared all over 4. That's it. So that should give us 314.16 times 10 raised to the power minus 6 meters squared. So that's the area of the pin. Now, to find the, so okay, look at this. If you go back to the problem, the question says, it says, while each, okay, let's start from this point. It says, while each of the pins at C and F has a 20 millimeter diameter and are made of steel with an ultimate strength in shear of 150 MPa. Ultimate strength in shear. Ultimate strength in shear 150 MPa, right? Now that which here we call this FU. Sorry, not we don't call that F. We call this TU. Sorry, TU, which is here. The FU is the force that results in the maximum force that results in that ultimate strength in shear, right? So looking at this, that's TU equals to the force FU over the area, right? I mean, typically we have force over area equals to stress, right? Now, but since this is shear, that's why we are using tau. Now, the ultimate strength in shear is so how this works is tau U multiplied by A equals to FU. FU now gives us the maximum force, right? Now, remember, for this expression, this is correct because if it's one pin. Well, here we have two pins. Hence, double shear. That's pretty important. Two pins, hence double shear. Right? So, therefore, what that means is FU is equal to 2A tau U, right? 2 multiplied by the area, it's the area is 314.16 times 10 raised to the power minus 6 times the ultimate strength in shear tau, that is 150 times 10, let's see, 10 raised to the power 6 too. Because here, this one, we've converted this unit to meters, right? And here is in PA. Right? If you're working with meters, you can use PA. If you're working millimeters, you can do MPa. You still resolve to the same units. That you just have to keep it consistent. So FU at this point here will be 94.248 times 10 raised to the power 3 Newton. So then we now have the maximum force, which is FU here. We have the maximum force in that component, in component CF, right here. So from the problem we have the force here, which is the force acting at this point here, and the overall force resulting from that this boat can withstand is FU, which is here too. So if we have this, we can then compute our factor of safety. So F of S here is equal to FU or FC of F, which is 94.248 times 10 raised to the power 3 Newton plus to CFC, I mean, the force due to that is 39 times 10 raised to the power 3 Newton. I have to confirm that to make sure it's right. Yes, that's this, right? So, of course, it's non-dimensional. The units cancel out, which is giving 2.4 Newton.